Okay, and we should see a little record dot there on the upper left-hand screen. And with that, I'm ready to turn over the presentation to Printology Group 1. It's all yours, guys.
Thank you. So we are Printology, and as Professor Trump stated, we're Group 1, and our members consist of Marilyn, Nicholas, Carlos, Isaac, Jose, and me, I'm Lorraine. So going into our presentation outline, we'll be discussing our hedgehog concept, our product overview, the analyses done on our subsystems, highlights and key features of our product, and our cost overview. So our hedgehog concept is that the Printology bioprinter really captures our passion for product versatility and our proclivity for a user-friendly product while minimizing the costs associated with product development. And it's important to note that while we are minimizing the costs associated with product development, we weren't willing to compromise any of the features required by the bioprinter in order to do this. So to provide an overview of our product, we will have 2 syringes in order to avoid cross-contamination of the cells that are going to be used for printing. We're going to have 3 hydraulic cylinders used for precise linear movements throughout the well plate while printing. We have a micropump that is used strictly for cell delivery, a belt-driven system used for cell retraction. Remote power sources will be stored in a secured enclosure aside from the microscope, and all of our power sources will be compatible with the smoothie board.
As Lorraine mentioned, we're using 2 distinct needles in our design, and it is to avoid cross-contamination. These 2 needles are spaced 10 millimeters apart, and they are custom made. They are threaded on top. And the purpose of that is because in order to have 1 needle at a given time within the LLS, we're using a spring pneumatic operated system that when the spring is uncoiled, the syringe is pulled up, and then when pressure is applied through the pneumatic system, the syringe goes down in order to be able to be put in the LLS. Aside from that, we did calculate the spring pressure necessary, and it was 0.4 megapascals in order to be able to lower the syringe to its max extent. Something else that we are considering is that our max fluid velocity would be 25 millimeters per second.
The next subsystem in our lineup is the printhead. The printhead is responsible for the movement of needles in the LLS, and it accomplishes by resembling a delta printer, where we use 3 hydraulic pistons to bring down our stage and bring the needles into the LLS. And then by modulating how much each one is extended or retracted, we can therefore control its orientation in the XY plane. So right now, our entire printhead is just below 200 grams. It's actually about 195 grams. And all the cylinders will be custom manufactured in-house because we couldn't find any other ones on the market that would fit our needs, that would be small enough and have the stroke that we needed. The hydraulic fluid is water because we did feel like in a laboratory environment, any other fluid would potentially be hazardous to any of the surfaces. So in case of a failure, water would be the fluid preference.
Right, so to make sure our design could actually print within the entire well of a 96 well plate, we created a MATLAB script that generates a mesh of our maximum print volume. So the first thing you notice from that mesh is that at the top most position, if you were to move the needle outward from the center, you actually have to also lower the needle to accommodate the length of each rod. And so you lose a little bit of that Z range of motion as you go to the outer edges. So the key points we had to hit for our print volume was that minimum travel along Z had to be at least 11.65 millimeters, and the minimum diameter of the area of the print volume had to be at least 6.94 millimeters. So that area is actually determined by the difference between the length of each rod and its horizontal projection, because that actually determines how much you can move away from the center. So the first thing we did was we designed the length of those rods and that initial ankle to make sure we could get a minimum diameter of 7 millimeters. And then once you have that, those design specifications in place, you know how much of that maximum Z travel is lost on the outer edges. And so then we designed the stroke of the hydraulic pistons to get 15.5 millimeters of minimum travel along Z, which gives us ample room to move within that entire well.
All right, moving on to the fluid transportation system. One of the key features we want to highlight here is that we have two separate systems for deposition and retraction of cells. So we went with a pump system for deposition because a pump system is more accurate than the linear system. For the pump system, we used a micro pump. By varying the voltage and the output diameter of the pump itself, we can vary the flow rate. Right now, to achieve the maximum print speed, the micro pump is able to achieve a 0.117 microliter per minute flow rate. And in order to prime the system, because if you insert the cells straight into the syringe and try to pump it, you're going to pump through air and it's not going to create laminar flow. So there would be a calibration process where the lines would be primed with an oil that wouldn't allow it to mix with the cells, and the oil would go through the system, moving the cells through the system up to the tip with it before initiating deposition.
As for the retraction, the bioprinter uses a belt-driven system that is composed of a tensioner to prevent the belt from becoming loose. Coupled with the belt-driven system, the bioprinter uses PVC tubing to transport the fluid from the cell retraction system at the printer stage to the remote system. Additionally, we also used color-coded quick disconnects for all the fittings in the bioprinter for quick assembly or disassembly for a better user experience.
In addition to that, based off what Jose mentioned, we are using quick disconnects for our tubing, and we're color coding it just to enhance our user friendliness, just to avoid any possible mistakes that could occur if the user were to disconnect any of them, and then to avoid them plugging it into the incorrect quick disconnect. In addition to that, we accounted for controllability of our system with what the smoothie board can handle. The smoothie board can handle 6 FET components and 5 stepper components. In our design, we're using the 6 FET components composed of 4 water pumps and 2 air pumps. The 4 water pumps are dedicated, 3 of them are dedicated for the print head, and 1 of them is dedicated for the fluid transportation, and the stepper motor is used to power the belt the belt system for fluid retraction. In addition to that, we have a user panel where we have an LCD and a potentiometer next to it that allows for the user to interface with our system, and through there they can be able to regulate different parts of what is going on, or like the printing operation. And the door is able to stay closed through magnets. That's how we're being able to close the door. And in addition to that, we position the power supply in a way that even if the cells or fluid does spill, that it doesn't reach the leads.
So when constructing a remote systems mount, we had to take into consideration the maximum temperature that the enclosure would reach. So in order to preserve cell vitality, we can only have a maximum temperature cell vitality is compromised at a maximum temperature of 40.5 degrees Celsius. So we performed the heat transfer calculations and we determined that our encasement would reach higher temperatures than that, like as a result of our power sources and the power supply being in there. So we decided to add 2 fans into it. So the necessary calculations demonstrated that we needed a fan with at least 0.65 CFMs. And we placed 2 fans which both meet those requirements. And one is located at the top of the remote systems mount where the pumps are in addition to the motor. And then an additional fan is located below, strictly with the power supply. So just going over it again, some of our highlights and key features are that we have distinct needles for extraction and retraction to minimize cross-contamination. We implemented a hydraulic system for precise linear motion. We plan on transporting fluid from a remote reservoir and allow for visibility of fluid levels. And all of our remote power sources will be secured in an encasement with easy access to all of the sources. And going into our cost analysis, we have an off-the-shelf part cost of $2,047.91, a raw material and manufacturing cost of $133.85, assembly cost of approximately $397.60, and that leads us to a total product cost of $2,579.36. And so now going into why our bioprinter should be selected for further development. Our design provides a user-friendly product while maintaining our total product cost below $2,600, all without compromising product functionality. By having this low cost, this provides a large profit margin for our sponsors while meeting all the necessary customer needs. So we would like to thank you for spending time watching our presentation, and all of us in Design Group 1 would like to sincerely thank the sponsors, faculty, and staff for watching our presentation, as well as providing us with the exciting opportunity to explore 3D bioprinting design.
All right, great. Thank you for that presentation. Very well done. Do we have any questions from our panelists?
I have a question. I still don't really understand why there's two needles. Can you elaborate more on why there are two needles and how they would cross-contaminate?
Yes, so if we were to use only one needle and we would just retract with it, and like we would pull back up cells and we would dispense them as well. Those cells have, number one, already been exposed to like the fluid. Number two, we also don't know what the use for those cells are. We don't know how they're being manipulated while they're in the well plate. For instance, if we want to see what a chemical does to a certain cell, what effect it has on it. So in as an example, like if they're running an experiment where they want to see how a chemical impacts a certain cell and then they want to retract it to be able to investigate that cell further, if we retract that into the reservoir where we have our healthy cells or cells that are meant to be manipulated, we're cross-contaminating them. So in order to avoid any conflict with that, we have two different syringes. However, we are planning for only having one at a time within the LLS. And the purpose of having them readily being able to retract up is to avoid recalibrating with every operation. So say they want to do successive sessions of deposition and extraction. So to see, let's say, how a chemical impacts the cell within 3 seconds of putting it in, then we can just deposit it and then extract it, or like retract it, I apologize. So it would be easier in this way.
Thanks.
Of course.
All right. So Dr. Nimi actually is teaching a class right now, but sent me, I'll put it into chat, the following 3 questions. And I realize that there's a spelling mistake, so let me get the spelling mistake fixed. There we go. Okay, so hopefully those have come through. So he wants to know first, what is your printer's feature size range? And then he wants to know, what is the needle velocity and fluid flow rate corresponding to the minimum feature size? And finally, what is the needle velocity and fluid flow rate corresponding to the maximum feature size?
So when it comes to the fluid transportation system and achieving these intended feature sizes based on the documentation and the research that we found that people had already researched, it doesn't depend on the diameter of the initial tip. So for feature size range, we would limit it to the maximum diameter just to limit it. So it'd be 200 micrometers for the, I guess, maximum feature size. And then the minimum that we initially started with when we were doing down selection of these needles was a 10 micrometer feature size. This is because eukaryotic cells tend to range between 10 micrometers and 100 micrometers of diameter. So we wanted to fulfill those requirements. When it comes to maximum velocity, we were able to calculate that based on the parameters. So the maximum velocity, as Marilyn mentioned, was 25 millimeters per second. And then the maximum flow rate that corresponds to that was the 0.117 microliters per minute to be able to achieve it without any discontinuity in the printing. As for the minimum velocity for the feature size, we did not compute that, since it depends on the initial needle speed that you choose would determine flow rate, which is, since those two are dependent on each other, you can go very slow with a slower Q rate and still achieve the same feature size, since those two variables are dependent upon each other. So it just depends how fast you want to print. There is a maximum cutoff, or for a specific value, I wouldn't be able to give that based on, it would depend on cell diameter and the density of the cells to very accurately tell what the printer is capable in regards to the minimum requirements.
All right, thank you. Other questions from the panel? Any questions then from the general audience? Any of the other folks who are here that want to ask something?
Can you go back to the X and Y system? Yeah. So how are you manufacturing? Are you manufacturing those arms, or is that off the shelf?
So good question. Similar arms exist on printers already, and some of them you can buy off the shelf. In this case, the ones that we needed were of a particular size, so these would be manufactured in-house.
And what material?
So right now, the entire structure is meant to be aluminum 6061 T6, and except for the ferrous materials. But yes, so that includes the arm, and that includes the cylinders.
And how are you attaching the, is that like welded to the plate, the little ends of the arms to that syringe plate?
Oh, so those are actually threaded in.
Oh, okay.
It's hard to tell from this image here, but the ball ends, it's a sphere, and then it's got a bit of a plate there, and then it's got some threads at the bottom and just thread into that plate there. So the way that you'd ideally put this together would be you have the plate, you thread in all the balls, and then you attach the arms.
Are you concerned about the tolerances at all? With like the stack up, with aligning all what's how many attachment points? Like 6 or 1, 2, 3, yeah, like 6 of those?
Yeah, so we were at first, and we were trying to keep tolerances as tight as possible, but then we looked into it, and so it turns out that since all the motion is really relative, and those are just going to be pivots, those are just going to be, it's almost like a ball joint, then the tolerances don't have to be too tight. So except for the initial calibration process. So.
And what are the size of those fasteners?
I believe they're M3. Yes, M3.
So you could disassemble this entire subsystem if you wanted to replace parts? Correct,
yeah. So that was one of our intents. We wanted to make sure that basically everything was adjustable by the user if they needed to, and that they could take it apart within seconds and then put it back together somewhere else with limited use of tools.
Oh, okay. How many total parts are there?
Right now, I can tell you. Sorry about that. Just give me 1 second. So in the entire assembly, there are 342 components.
Wow,
Yeah,
it's a lot.
that's a lot. Yeah. That includes the remote mount, by the way.
Oh, the remote as well. Okay.
Yes.
Oh, okay, so that whole like box.
Correct. That includes the entire
Oh,
box.
okay. I really liked how you thought about the user interface and put it all in a nice box there. That you're like kind of one of the only teams that has really done that, so that's kind of cool.
Thank you. We appreciate that. We just wanted them to have something they could connect to and not worry about the inner workings too much, unless they wanted to.
I have a question regarding assembly time. Did you just say you had 342 components, if I heard correctly?
That's correct.
Did you calculate the assembly time for the 342 components? And also, they're pretty minute in terms of their actual dimensions. Like, are you gonna like put them together with like a tweezers or something, or how did you plan on assembling it?
So the thing with the 342 components is that those are the components within the CAD model. And if you have any sort of motor or any sort of assembly that comes pre-assembled from, let's say it's an off-the-shelf part or something like that, then those components are factored into the calculations in the CAD. So ultimately, we don't have the user would not have to assemble 300 and something components. It would be less than that. And if you give me like 1 second, I can check our bill of materials and I can give you a more precise, like a more exact number on how many actual parts we would be ordering for this printer. Give me 1 second, because the components are as far as the CAD model goes, but I don't know if you understand like what I'm trying to explain, where a lot of the parts come pre-assembled, but all of their individual components are factored into the total components for the CAD model.
That I understand. That completely makes sense.
Yeah.
Also, to echo what one of the panelists just said, I like the box that you put all those other components in. It's pretty aesthetically pleasing, and also something
thank you.
we didn't do for our CAD model. So I appreciate the CAD work that went into that.
Thank you so much.
So just to clarify, so that I understand what's going on, when you guys calculated your assembly time, because I remember that slide from somewhere, you guys had a cost associated with assembly. You guys are not calculating that assembly time or cost based on 320 or whatever the.
Correct. Yeah, that's correct. So based on the bill of materials, we have roughly about 94 parts. So let's say somewhere between 90 and 100. So we calculated our assembly time based on those 94 parts. And some of those parts, even though they have to be ordered separately, they will reduce our assembly time because some of them come already sort of assembled and there's not as many fasteners as need to be added to them, and they just need to be adapted to better fit our system. So that's why our assembly time isn't higher than what you would expect for an assembly with like 300 something components, because our assembly time is really based on what we're ordering with our bill of materials, and that would be 94 components, including fasteners and fittings and whatnot.
Okay, and so remind me what the assembly time was again? So
I don't have the exact number for the assembly time right now, but I believe our assembly cost is around, about just under $400.
Okay. $400. I'm just going to do a little mental math here, but if anybody else has a question while I'm calculating, feel free.
I had a question regarding how the actual CAD was done. Did you guys do a bunch of sheet metal bends and make that entire box for the box that holds everything with the glass? And also my question was regarding the microscope as well. Did you CAD that microscope as well? Or are these OTS, is the box OTS and is the microscope, I guess, GrabCAD?
So good question. The microscope, yeah, definitely GrabCAD. We just want to put it in here so we could have the reference dimensions and we could show what it would look like when it's mounted. And then the remote mount was completely custom made. And the plan is just to get, there's a total of 6 pieces of sheet metal that go into it, and then it requires shearing, bending, and then punching operations to bend it all into shape, and then a lot of fasteners. and rivets.
Yeah, the box that you guys made is really clean looking. We were talking about in our group how nice the box looks.
Thank you. We appreciate that. We tried to give the user some. If they were going to have it in their lab, we wanted it to be at least a little bit nice to look at.
Can someone answer the question in chat when they ask how are you going to zero the bioprinter?
Yes, we can. We did consider, because we were in a meeting with Dr. Traum, and he brought up, he had mentioned zeroing the printer, and he wanted to pursue us. The current options that are available in the lab are by visually zeroing it in above the well plate before initializing printing. We saw issues with that initially our design was just zeroing it by eye and coarse movements, but then we considered we wanted to be a more user-friendly experience. So we started exploring avenues. We were very limited in exploring since we couldn't see the actual physical microscope and see which knobs it was and which model it was. I did a rough idea, but I couldn't get the dimensions exact because we didn't get to physically see the microscope, but I can share my screen real quick. It should just take off yours, right, Lauren? Okay, cool. So I don't know if you guys can see this. No? Huh. Can you guys see it? Or, there it goes. Got it. All right, so this is the same initial CAD model, but what we decided to do is modify the knobs themselves to include an encoder. So a first initial way of calibrating this would be, we know the relative position of the needle due to the height of the dovetail relative to the mount. So if we lower Z all the way, we already have Z calibrated. And we would just put encoders on each of the knobs, taking them to the maximum extents and zeroing it, because we know the positions of the actual, how far in X and Y it can move, and where the well plate is located relative to all of that. So in the knobs here, we would include encoders that could be mounted to the smoothie board and display on a DRO an active reading of where you are in 3D space, and have a visual map to show where you are in terms of well plates and what dimensions you need to achieve to reach each well plate. Another idea we had for calibration that I thought was pretty neat is using sort of like the idea of garage door sensors, how when you break a laser, it sends the signal that you cannot open the garage door. So following that, I pursued that, and we came up with these reflective photosensor, they are called laser retroreflective sensors, and implementing them here. Let's suppress all of these. It would be able to zero it using the laser. Whenever the needle would break the laser, you would be zeroed in on the first well. Once you break both lasers that are mounted at different heights, allowing for us to zero in on X and Y on the first well plate. And once you know where the X and Y is zeroed on the first well plate, you know every single well plate in relation to the first one. You just need to set that initial reference frame. And you'd be able to know the, I think I deleted that instead of unsuppressing it. Let me unsuppress. There we go. So once you zero in on this first well plate where they cross, you would first zero in the X or Y axis, breaking that laser. Then you have that zero set. Then you would move to cross the next laser. And once you have those two crossed, and these lasers are accurate to the nearest millimeter. So we'd be able to get within 1 millimeter accuracy of the needle relative to the center. So the encoder is a modular encoder, and it has in order to get higher tolerance, I looked up very high precision encoders, and it's a 4096 pulse per revolution encoder. So I believe that will give us the accuracy we need to know relative to each well plate. We can get very close to the center. Again, you're not going to be printing directly on the wall because you're going to be within a certain diameter, a certain range away from the edge to print within the LLS and allow the cell to not be affected by the walls of the well plate. So I believe with either of these setups or the combination of both, this laser setup would require the combination of both depending upon how accurate the user wants to be. So for the encoder setup by itself, it would cost $87.92 in addition to our original part cost, and including the laser setup with the encoders, it would be $321.62 to use the laser to zero in.
And just to jump in on that.
Sorry, no. Continue. I was just gonna ask another question when you're done.
Oh, sorry about that. Just to jump in on that real quick. I got a question about the first option. And so we do realize that a customer requirement is to not have anything near the microscope stage. So one of the ways the very first option that we described was if we know that the dovetail mount stays constant and stays in the same place, if we move all of the water out of the top of the cylinder and into the bottom, we can retract the syringes all the way up as far as they can go in the Z, and they'll also land in the center of the XY. So we'll know the position of the syringe relative to the dovetail. Therefore, we know it relative to the microscope, but the stage can move. So if we can, sorry about that. If we can put the stage all the way up in a corner to as far as it can travel, and then we can let the user press a button that will let them know that it's already set up, then the encoder can start counting relative from there. And then you can move from well plate to well plate, and the reading would be on the LCD as well. So that's just to clarify that, but everything else is the same. So sorry about that, Jeremy. Didn't want to interrupt you.
No worries. I was just wondering, I was a little confused on how you actually achieve the positioning. Is it based upon the laser or a combination of the laser and another component? And the thing that confused me is that you said it achieves 1 millimeter of accuracy. Is that the maximum resolution that you're able to achieve, or can you get down to a better resolution than 1 millimeter?
With the photosensors on the market, that was the highest resolution one I could find, OTS. I'm sure there's other options out there, but due to, I guess, limitations of like custom making labs that I'm unaware of as an engineer, because I obviously I've never been familiar with it. I did the research I could to find what I could that's easily accessible, but as far as custom labs that could make more accurate laser measuring devices, I could not find that.
So just to jump in on that real quick, to address your first question, there would be two different methods to do this. The first one just requires that you either add an adapter or change the knob itself with an encoder. And then the user will be guided through a set of options on the panel so that they can zero it. The second option included on top of the encoders, they included 2 laser systems to guide with calibration at the very beginning of the process. So one of them includes just the encoders, and then the other one includes the laser system if they would prefer that. So again, we're still experimenting with that.
Thank you.
Okay, and I'm just looking at the time, and out of respect for everybody's time this afternoon, I think we'll wrap it up there because we're 8 minutes over where we needed to stop. So with that, I will stop the recording.